Hi, my name is Jessie Chen, and I'm a PhD student at Princeton University working with Meng Chang. I'll be talking about resource allocation for LTE Multicast, or EMBMS, group partitioning and dynamics. Content delivery over cellular networks is an ever-increasing challenge. In general, the radio access network is the bottleneck and a significant source of latency, so multicast on the cellular last mile can improve utilization of scarce wireless resources and deliver large amounts of data to users. EMBMS is the multicast standard for LTE. It's targeted towards service areas with common user interests, such as sports stadiums or parades. For example, in February 2014, Verizon demonstrated EMBMS at the Super Bowl. In the LTE architecture, EMBMS introduces a new entity, the MCE, or Multicast Coordination Entity. The MCE coordinates multicast transmission amongst the base stations, or eNode Bs, in the service area. This service area may encompass multiple cells, as shown in the figure. The multicast resource blocks, shown in yellow, are common across all base stations. In contrast, the unicast resource blocks, shown in blue, can be flexibly allocated to the unicast users at each base station. Let me show you a toy example to illustrate our problem. There are two control knobs. Which users interested in multicast content should be placed in which multicast group, and how many resources should be given to each unicast user and multicast group. Our goal is to maximize total proportional fair utility across all users. Each user is associated with a coding scheme, which reflects the user's channel conditions. Users with better channel conditions can receive more bits per resource block, and vice versa. In our tour example, there are 3 yellow users interested in multicast content and 1 blue unicast user. User A has poor channel conditions, user B has better, user C has the best, and unicast user D has average channel conditions. In case A, let's suppose that there is no EMBMS service and all users are forced to use unicast. In this case, each user is allocated an equal share of resources and receives rates proportional to their coding scheme. In case B, let's say we have EMBMS service, and we naively group together all multicast users into a single multicast group. This causes user A's rate to increase because she shares resources with the group, but user C's rates suffer because she is forced to use the same poor coding scheme as user A. Finally, in case C, we might do a better grouping and put together users B and C, who have similar channel conditions, into their own group. We can see that this improves the total utility. Thus, we can see that both the control knobs, group formation, and resource allocation must be optimized to maximize global utility. In this project, we study the joint optimization of multicast resource blocks and user grouping. We formulate this as an optimization problem. We aim to maximize the proportional fair utility for both multicast and unicast users across all cells in the EMBMS service area. Our constraints are: the total amount of multicast resources allocated cannot be greater than EMBMS system constraints. All multicast users must receive all content, and all multicast users must belong to a group. We solve this problem through a combination of convex optimization and dynamic programming. The previous solution assumes that the network operator has full control over its users and can place users in multicast or unicast transmission schemes as it pleases. In practice, this is clearly not the case. Users may choose to leave their multicast group and switch to unicast, or vice versa. We assume that each user decides to switch to multicast or unicast based on her received rate. We then ask the question, when will users deviate from the globally optimal solution decided by the operator? Let's return to our toy example to see how this works. In scenario B, user C receives a rate of 9 when she is part of the multicast group, versus a rate of 12 when she was a unicast user in scenario A. She will prefer scenario A to maximize her rate, at the expense of global utility. In our work, we generalize this toy example and improve the conditions under which users desire to switch, and we also are able to bound the number of switching users. Thank you for your interest in our work. Please feel free to contact me at jessec@princeton.edu if you have any questions or comments.